Welcome back. This is the second video for experiment 6. So now we're going to take a look at polyatomic ions, which, as the name implies, are just ions that have two or more atoms. And in most cases, those atoms are nonmetals. They're almost all going to be anions. The only important cation is this one right here, which is ammonium. It's very important that you not confuse ammonium, NH4+, with ammonia, which is NH3, a neutral molecular compound. And so there are many of these, some of which I imagine you've heard of by now, the hydroxide ion, the nitrate ion, and the sulfate ion being just among the more familiar, as well as phosphate. And page 61 in the lab manual has a fairly good list of some of these ions. Now, one of the things that you have to deal with when you're working with these polyatomic ions is you want to strive to see them as a unit. In other words, when I see, say, nitrate, I don't see one nitrogen atom and 3 oxygen atoms in a formula. I see the whole thing together as a nitrate ion. And the same idea with hydroxide. I don't see an oxygen and a hydrogen. I see them together as a unified whole. And if you can do that, it will make it much easier to name these compounds. So there really isn't anything new in terms of the way the naming rules work. We simply say the name of the cation, and then we say the name of the anion. So here we have ammonium bromide. Ammonium, you'll recall, was NH4+. Bromide is -1 charged, so this would be a 1-to-1 formula. And then sodium nitrate. Sodium is +1. Nitrate is -1, so they come together in a 1-to-1 ratio. Calcium sulfate. Calcium is in group 2, so it's always +2 charged. Sulfate has a -2 charge, so they come together 1-to-1. Now, there is one problem though, and that is, what if we need to show 2 or more of a polyatomic ion? So for example, let's say I needed NO3, but I need 2 of them. I can't just write NO3 because that looks like 1 nitrogen and 32 oxygens, right? So what we do is we put parentheses around the polyatomic ion and put a number after the parentheses to indicate that you have more than one of them. So for example, magnesium nitrate would be a good example of this right here. Magnesium has a +2 charge. Nitrate has a -1 charge. So we need 2 nitrates to balance out magnesium's charge. So instead of NO32, which I warned you about, you put NO3 in parentheses and a 2 on the outside. And here is a compound with a variable charged metal, iron 2. So if iron is +2 and phosphate is -3, the formula will be iron with a 3 after it and phosphate with a 2. Make sure that you can see how those charges cancel out. Now, when you first start learning about using parentheses, a lot of students have the temptation to start going overboard and using parentheses everywhere, and I really need to urge you not to do that. So they are only used around polyatomic ions. So you'll never see chlorine by itself, for example, in parentheses. Has to have 2 or more atoms like this. And you only use them when there are 2 or more of the ion in a formula. In other words, you would never have a set of parentheses and then not have a number. There always has to be a number 2 or greater after the parentheses. If you go back and look at all the work you've done so far in parts A through C, you should not have a single parenthesis anywhere in there because we haven't looked at polyatomic ions yet. There would have been no reason to do that. So please make a quick double check to make sure that you haven't put in any parentheses. So now let's take a look at part D. And again, the instructions are very similar to those in Part B. So when you're asked for the physical properties of the compound, look it up on Wikipedia. And I'm not going to repeat this because you already should know this. So then you'll want to complete the two tables on page 71. And since these are still ionic compounds, the 4 essential rules still apply. And finally, don't go all crazy about writing parentheses. Only around polyatomic ions, and only when there's 2 or more of them. So you can go ahead and pause the video at this point and work on Part D. And when you're done, I will continue on to the material for Part E and then Part F. Okay, continuing on. Molecular compounds. So as the name implies, these are compounds which form molecules, which means that they are going to be held together by covalent bonds instead of by ionic bonds. And the easiest way to recognize these types of compounds is that they contain only nonmetal atoms. Now, there is a big difference here with molecular compounds and ionic compounds. With ionic compounds, we saw that they always came together in a ratio that would cancel out the total charge. Now, in these compounds, there is no concept of charge. So what that means is many of these nonmetals can come together in totally different ratios. And just for one set of evidence on this, here look at what nitrogen and oxygen can come up with. So 1 to 1, 1 nitrogen to 2 oxygens, 2 nitrogens to 1 oxygens, 2 nitrogens to 5 oxygens. I know there's also N2O4, so there's other ratios. And sulfur and oxygen can come together as SO2 and SO3. And so we have to take that into account when we are naming these compounds. So for example, we can't just call this sulfur oxide because we don't know which one we're talking about, nor more than we can call this nitrogen oxide. We have to know which one we're referring to. So another important difference here is that because these can come together in different ratios, we do not need to write molecular compounds in the lowest whole number ratio. In these particular examples, they all are written in their lowest whole number ratio, but it wouldn't be unreasonable to have, for example, S2O2 if such a compound existed. We use prefixes in the names to tell us exactly how many of these elements are in each formula. We are only going to focus on what are called binary nonmetal compounds. Binary means that there are only 2 different elements in them, and nonmetals means the elements must be nonmetals. So like you saw a moment ago, compounds with nitrogen and oxygen, or sulfur and oxygen. The prefixes that you're going to need to know for numbers 1 through 8 are on page 63 of the lab manual. They're also listed in your textbook. So the way to name these compounds is you put a prefix in front of each element's name to tell you if there's 2 or 3 or however many of that element. So if there's 2 nitrogens, it would be dinitrogen, or if there's 4 nitrogen, it would be tetranitrogen. And then, as with ionic compounds, you're going to still change the ending of the second element to "ide", I-D-E. That doesn't mean it's an ion. This is just a naming convention. So it turns out we do not use the prefix mono if it's in front of the first element. So that means that you will never begin a name with mono, but mono might appear in the middle of the name in front of the second element. So in this case, we have 1 phosphorus and 3 chlorines, so it's going to be phosphorus trichloride. So you'll notice there's the prefix tri. And we don't say monophosphorus trichloride, so you'll never see that mono in the front. Another weird rule just has to do with vowel combinations. And when we have oxide, you never want to have 2 O's right next to each other, or an A and an O right next to each other. you're just going to replace either of those with the letter O by itself. So, for example, CO, we don't begin with mono, so it's carbon, and then one oxygen would be monoxide. So it's carbon monoxide, only one O, and not carbon monoxide with two O's. And here's another example. We have two nitrogens, so dinitrogen, and then four oxygens would be tetroxide, but we prefer just having tetroxide instead of having the A and the O together. So some of these instructions are going to be the same as for Part B, but there are going to be a few important differences. So you are going to look up the compound on Wikipedia. In this case, for Part E, it asks you to look up the properties of water. And you don't want to look up water by itself on Wikipedia because it won't give you the information you need. You want to look up properties of water specifically. And then you will see the properties and the picture of the compound. Again, densities need to be in grams per milliliter, melting points in degrees Celsius, and then you'll want to complete the tables on page 71 and 72. Now, in the previous slides, I've been telling you to always watch out for the rules on ionic compounds so that you follow the 4 important rules. Since these are not ionic compounds, those rules do not apply at all for Part E. So go ahead and pause the video and complete Part E. And when you're ready, you can unpause it and continue. Alright, continuing on to the material for Part F. We're going to go in a significantly different direction here. So we're going to leave the topic of naming and focus ultimately here on molecular shapes. So an electron-dot formula, which is usually going to be called the Lewis structure, tells us which atoms are bonded to which other atoms, and it will ultimately tell us something about how the angles are positioned within those molecules. Now, when you're drawing the Lewis structures, the most critically important thing that you need to do is you're going to need to follow some steps, and always in order. You don't want to skip around on those steps, because if you do, you're likely to make mistakes. So the steps are given in the textbook on pages 95 to 97. That's the Smith textbook and not the lab manual. And so we're going to practice with 2 molecules to review those steps. So we're going to have ammonia, NH3, and then we're going to look at hydrogen cyanide, which is HCN. So I'm going to go ahead and start here with ammonia, NH3. So the first thing we're going to do is figure out the relative placement of the atoms. So I'm going to put nitrogen in the middle, and then I'm going to surround that with hydrogens. We say that the nitrogen is the central atom. It is being surrounded by these. In most cases, the central atom will be the first element, but that's not always the case. The general rule is it's the least electronegative atom other than hydrogen. Hydrogen can only make one bond and therefore is never the central atom. So therefore we have nitrogen here and 3 hydrogens. We now do some electron bookkeeping. So we have to figure out how many electrons come from each atom, and specifically how many valence electrons. So nitrogen, there is 1 nitrogen in the formula, and it has 5 valence electrons. It's in group 5A. So 5 valence electrons from nitrogen. And hydrogen, there are 3 of them. And hydrogen's group 1A, so it has 1 valence electron, only 1 electron period. So this gives us a total of 8 electrons which will appear in our structure. So the first thing that we want to do is connect all these atoms with single bonds. And each one of these bonds has 2 electrons in it. That's what bonds are made of, electrons. So 2, 4, 6. I am now down to having 2 electrons left. So who can take electrons? Well, hydrogens can never take lone pairs. So the hydrogens are full. They have their duet. They meet the duet rule. We're done with those. Nitrogen, on the other hand, has 2, 4, 6 electrons around it. It does not have an octet. So to get to 8, we're going to put a lone pair. That's a pair of electrons on the nitrogen. And that takes the number of electrons we have down to 0. Okay, so if we look carefully at this, nitrogen has an octet, 2, 4, 6, 8. It has a total of 8 electrons that we started with. We are done with the Lewis structure for NH3. Now, let's take a look at the one for hydrogen cyanide. So first, which of these is the central atom? It's never going to be hydrogen. So between carbon and nitrogen, which is less electronegative, that's easy to figure out by looking at the periodic table. The one that's closer to fluorine is more electronegative, and that would be nitrogen. So carbon is less electronegative. So we're going to put carbon in the middle here, and I'm going to space these elements out. And now let's go ahead and draw in the connection between them. So let's take a look at the electrons. There is one hydrogen, and hydrogen has 1 valence electron. So that's going to be 1. Carbon, there is 1 carbon in the formula, and carbon is in group 4, so it has 4 valence electrons. And nitrogen, there's only 1 nitrogen in the formula, and it has 5 valence electrons. So that's a total of 10 valence electrons. So I've already drawn in 2 over here and 2 over here. So I'm done with 4 electrons. I'm down to 6. So now I start drawing the electrons as lone pairs. The atoms on the outside, the more electronegative atoms, get the lone pairs first. So nitrogen only has 2 electrons around it, so let's give it 2, 4, 6. And now we're down to 0 electrons. Well, this is great for nitrogen. It now has an octet. It's totally surrounded. 2, 4, 6, 8. But the problem here is for carbon. 2, 4, we need to get to 8. We can't put lone pairs on carbon because we're out of electrons. You have 0 electrons left. So when this kind of a circumstance happens, what we need to do is have carbon go next door and borrow those lone pairs, make them into double or triple bonds. So since carbon is going to need 2 more bonds to get to an octet, I'm going to get rid of those 2 electrons, and I'm going to get rid of those 2 electrons. Oops, got rid of part of my N as well. Oops. There we go. So I got rid of 2 electrons here, and I make those into a bond. You'll notice carbon still only has 2, 4, 6 electrons. So I got rid of these electrons here. I'm going to make those into a bond. And so now I have a triple bond. Carbon has an octet, 2, 4, 6, 8. Nitrogen has an octet, 2, 4, 6, 8. And how many electrons are there total? 2, 4, 6, 8. Plus this lone pair is 10. So I have the right number of electrons. And now we continue on to shapes. I am going through this rather quickly because I have assumed that you have covered this in lecture. So it's meant to be like a review. So the shapes of molecules and their relative bond angles can be determined from 2 pieces of information. the number of atoms that the central atom is bonded to. Notice not how many bonds it's making, but how many atoms is it bonded to. And the number of lone pairs bonded to the central atom. These numbers taken together are basically going to tell us the number of what we call electron pair groups. So ultimately, to figure out the shapes, what we do is we look up the shape that has the correct number of atoms and the correct number of lone pairs, and then just match that using either the information on page 64 of the lab manual or page 101 of the textbook. I'm going to show you right now page 101 of the textbook, which accidentally leaves out a shape, but it won't be important for today. So total number of electron pair groups, that's just the sum of these columns here. So number of atoms the central atom is bonded to, number of lone pairs, 2 plus 0 adds up to 2. Go down to here, 3 plus 1 adds up to 4. So that's total number of groups. We're assuming the central atom is going to be this atom here, A, and these red groups stand for the atoms that A is bonded to. So in this picture, atom A is bonded to 2 other atoms, and you see no lone pairs drawn on atom A. So therefore, we would say atom A is bonded to 2 atoms. We don't include it itself, and it has no lone pairs. And in that kind of a circumstance, we get what we call a linear shape. And for linear shapes, we have a bond angle of 180 degrees. If the central atom is bonded to 3 atoms and has no lone pairs on it, that is called a trigonal planar shape. You can't call it just trigonal because we see the word trigonal comes up later. So those have 120 degree angles. If we have 4 atoms bonded to the central atom and 0 lone pairs, then we get what is called a tetrahedral shape. Now, the way this is drawn is to show you that the molecule is actually in 3 dimensions. And this wedge is telling us that this atom is coming out at us, and these dashes tell us that that atom is going away. You do not need to draw wedges and dashes for this experiment. You could have just drawn A in the middle and the 4 atoms on different points as far away from the central atom and each other as possible. And this tetrahedral shape has 109.5 degree bond angles. We have trigonal pyramid or trigonal pyramidal, which is what we get when the central atom has 3 atoms bonded to it and 1 lone pair. And we have bent, which is what we get when the central atom is bonded to 2 atoms and has 2 lone pairs. The one shape that was neglected here is that there is another version of bent. And you can get bent also when there is 2 atoms and only 1 lone pair. So that normally would have appeared here in the table. That would have been 3 groups, 2 atoms, 1 lone pair. And that would have been bent, but with 120 degree angles. None of the molecules you're going to see today, however, will be that form of bent. They're going to be one of these 5 right here. So let's go ahead and take a look at the molecules that we just built and figure out the necessary information for them. So let's practice assigning shapes, and I want to do this using the examples that we just looked at, ammonia and hydrogen cyanide, and I want to do this in exactly the same format as what you're going to be asked to do in Part F of the lab report. So the first thing that you're going to be asked is the number of electron groups. Remember, that is the number of atoms bonded to the central atom, which is nitrogen here, plus the number of lone pairs. So nitrogen has 1, 2, 3 atoms plus 1 lone pair. So a total of 4 electron groups. Now, the way your lab manual then proceeds to do this is it'll ask you for the electron group arrangement. And if you look in the lab manual, whenever there's 4 electron groups, that's called tetrahedral. even though the shape is not tetrahedral. If there are 3 groups, it is called trigonal planar, and if there are 2 groups, it's called linear. Just go ahead and look in the lab manual, the last page of material right before the procedure starts, and you'll see that. The number of bonded atoms, so specifically how many atoms is the central atom bonded to. So nitrogen's bonded to 1, 2, 3 atoms. So it's bonded to 3 atoms and has 1 lone pair. So the shape is then called trigonal pyramidal or trigonal pyramid. We haven't covered polar or nonpolar yet, so I'll come back to that. How about for HCN? The carbon is bonded to 2 atoms, and the carbon, remember we only care about the central atom, has no lone pairs on it. We don't care that nitrogen has a lone pair. So the carbon is bonded to 2 atoms plus 0 lone pairs, so a total of 2 electron groups. And the lab manual tells you that we call that a linear electron group arrangement. How many atoms is carbon bonded to? It's bonded to 2. Doesn't matter that there's a triple bond here. So it's just how many atoms is it bonded to? 2. And so when an atom is bonded to 2 other atoms and that central atom has no lone pairs, that's called the linear shape. And now we're going to finish off with polarity. Now, first we'll look at the polarity of the individual bonds. We know that covalent bonds are polar if they have a fairly large difference in electronegativity between the atoms which are bonded. So if the difference in electronegativity is greater than 0.5, they are going to be polar. So the most important thing is to recognize the ones which are not polar. So the nonpolar covalent bonds that you see are between carbon and hydrogen. Carbon has an electronegativity of 2.5, hydrogen 2.1, so the difference is 0.4. So that would make this a nonpolar bond, any carbon-hydrogen bonds. And whenever you have identical atoms bonded together, those are nonpolar bonds. So carbon to carbon, nitrogen to nitrogen, hydrogen to hydrogen, etc. If a molecule only contains nonpolar bonds, we would expect it to be nonpolar overall. Now, what if we have polar bonds and nonpolar bonds? Well, or just polar bonds. Then what we're going to need to do is look specifically at the polar bonds. If they're identical, meaning same atoms, like carbon to chlorine or carbon to fluorine, or nitrogen to oxygen or something like that, if they are all the same and they're oriented in opposite directions, then we say that the dipoles cancel out and the molecule overall is nonpolar. Let me be very specific about this. Oriented in opposite directions. This means that if the molecule has 4 electron pair groups, that those all have to be identical bonds and they're all pointed in opposite directions. If a molecule has polar bonds and they're not all the same, or if the bonds don't cancel out in opposite directions, the molecule will generally be polar. Now, the interesting thing here is if there are lone pairs on the central atom, that essentially guarantees that the molecule will be polar, because remember what we said here, you need all the groups to be oriented in opposite directions. If there is a lone pair on the central atom, there's no way that you can cancel out in the same direction that the lone pair is. And so therefore those would be considered to be nonpolar. So we're going to go ahead and continue on and determine whether these molecules we just looked at were polar or nonpolar. So let's look at this. We have nitrogen bonded to hydrogens. Those are all polar bonds. And there is nothing on this side to oppose this. As I said, if there's a lone pair on the central atom, then there's no way of having all the groups be opposites. We have 4 groups, but only 3 hydrogen atoms. And so therefore, there's nothing to push back on this side, so this molecule is polar. If we look more specifically, the dipole moment goes up towards the nitrogen. And now if we look here at HCN, what about this? Well, the carbon-hydrogen bond is essentially nonpolar. Carbon-nitrogen is polar, so the electrons are going to be pulled towards the more electronegative nitrogen. So there is a dipole moment going that way, and the molecule is, in fact, polar. This is probably the most difficult part of this whole lab, and it just takes lots of practice with molecules to start seeing whether molecules are polar or nonpolar. So finally, we look at part F in the experiment. So you'll want to complete the table on page 72 and use the exact same format that I just did for ammonia and for hydrogen cyanide. It would be preferable if you start by drawing your structures on a separate sheet of paper so that you can figure out how the molecules look and practice getting them nice and neat, and then copy those over to the report sheet. Otherwise, it makes it very difficult for us to grade and interpret, and you don't want that when we're trying to figure out your score. So please, a separate sheet of paper first, then copy your structures over. Vitally important, all atoms other than hydrogen must satisfy the octet rule. So every atom must be surrounded by 4 electrons. That would mean 4 bonds, or 3 bonds and a lone pair, or 2 bonds and 2 lone pairs. But they must satisfy the octet rule. To that end, I do not want you to go searching for the answers to this on the internet, because some of the structures we're going to assign you, we find out in more advanced chemistry classes, can get to exceed the octet rule. And if you're drawing those, then I kind of know that you went and looked them up on the internet. Don't do that. Follow the procedure that you've learned. And trust me, I've been doing this for many, many years, and it is totally obvious when you went and looked these up on the internet instead of doing them on your own. You'll need to make the lone pairs very, very clear. So nice, dark, clear dots. And then I'm going to go ahead and show you some virtual models right now, which you should compare with your Lewis structures at the end to see how much they resemble the molecules that you have drawn. Now we're going to look at some molecular models. We're going to start with water. These are all from part F. You'll notice that the white spheres stand for hydrogen atoms, and the red sphere stands for oxygen. Those dots that were there just a moment ago stood for lone pairs. Sometimes we'll show them, and sometimes we will not. This is the next molecule, sulfur difluoride. I'm not showing the lone pairs on this one. The sulfur is the atom in the middle, and the fluorines are the 2 atoms to which it is attached. Next, we look at nitrogen triiodide. That little dot at the top is a lone pair. That's what it's standing for. And the blue is the nitrogen, and the purple are the iodine atoms. You'll notice I got rid of the lone pair there. So now if we drag it down more, we can clearly see how it's kind of a triangle shape, and it's very pyramidal, much like a pyramid. The next molecule is silicon tetrabromide. So silicon is in the middle, and the 4 atoms to which it is attached are bromine atoms. Here's a different perspective of it. Here we have sulfur trioxide. You'll notice that where we have the 2 lines, that stands for a double bond. You'll notice it's a nice flat, planar molecule. So notice we have a double bond there and 2 single bonds to the oxygen. And we're going to end with carbon dioxide. You'll notice that there are double bonds on either side of the carbon, which is in the middle. Thank you for watching this video, and this concludes Experiment 6.